In this lecture, I'm going to introduce you to this next section of the course, which is all about the explore-exploit dilemma and different algorithms for solving it. To start, I'm going to introduce you to the problem that we're trying to solve, and then in the rest of the lecture, I'll outline what we'll cover in the rest of this section. So, like many problems in probability, the typical analogy we use for the explore-exploit problem starts with a casino. Let's pretend that we go into a casino and we have a choice between two slot machines. Let's also assume that these are very simple slot machines. You either win or you lose. There's no in between. And if you win, the prize is always the same. So without loss of generality, we can say that winning gives you $1 and losing gives you $0. Let's now go through an imaginary sequence of events, and what I would like you to do is to think about how you would choose which machine to play. So starting out, all we see is two machines. We know absolutely nothing about them other than what I just told you. You can either win or lose, and when you win, you get $1. At this point, how do we choose which slot machine to play? In fact, it doesn't matter. Because we know nothing about either machine, any choice would be equivalent. So let's pick slot machine number 1, and let's say, oh no, we lost. So what's our next move? At this point, we know something about slot machine number 1. We know that we played once, and we lost once. What do we know about slot machine number 2? Well, we still don't know anything. Again, I want you to think about which slot machine would you pick to play now? Most of us would probably pick number 2. And it's useful to think about why. Why pick number 2 instead of number 1? Well, we all know how to calculate probabilities. The probability of success would be the number of times we won divided by the number of times we played. In the case of slot machine number 1, that would be 0 out of 1, which is 0. But for slot machine number 2, it's 0 out of 0, which is undefined. And something in our intuition tells us that undefined is better than 0, even though numerically you can't compare these numbers. Okay, so let's say we played slot machine number 2 and we won. Here's where we stand now. We played slot machine number 1 once and we lost that one time. We played slot machine number 2 once and we won that one time. So which one do we play next? Again, most of us would pick slot machine number 2. It appears so far that slot machine number 2 has a better chance of winning at 100% than slot machine number 1, which has a 0% chance of winning. At this point, you should be thinking statistically. Is there anything wrong with my calculations? Is it wrong for me to assign 0% to machine number 1 and 100% to machine number 2? You should recognize that these estimates are exactly what we would call the maximum likelihood estimate. But ask yourself, is there something incomplete about these measurements? Since we decide to play slot machine number 2 again, we observe the result, and unfortunately we lose. But if we look at these machines in a maximum likelihood way, machine number 2 still looks better. Machine number 1 has a 0% chance of winning, and machine number 2 has a 50% chance of winning. So let's play again on slot machine number 2. Alright, so we play slot machine number 2 again, and unfortunately we lose yet again. At this point, our updated probability of winning for slot machine number 2 is 33%. Note that this is still better than slot machine number 1. So if we use our maximum likelihood estimate to greedily choose which machine to play, we will choose machine number 2. So we play machine number 2 again, and unfortunately we lose again. Now we've lost 3 times and won once. So the probability of winning with machine number 2 is 25%. At this point, if I ask you, which machine do you decide to play next? There would be more disagreement about whether to play machine number 1 or machine number 2. And by that I mean relative to the first time we chose machine number 2. As you recall, the first time we chose to play machine number 2, We didn't know anything about it. We hadn't collected any data at that point, so our estimate of the win rate was 0 out of 0, which is undefined. Now we have more data. We've won once and we've lost 3 times, so we calculate our win rate as 25%. On the other hand, for machine number 1, our calculated win rate is 0%, but we've only played once. We know that this is somehow less accurate, so we might want to play machine number 1 again so that we can be more certain. I want you to think about what kinds of mathematical tools do you use in your mind to come to that conclusion? Why do we go against making a greedy choice based on the maximum likelihood estimate of the win rates? So if you're a traditional statistician doing frequentist A/B tests, you would be yelling at me saying that I'm approaching this problem all wrong. The correct way, you say, would be to decide before even walking into the casino how much data I should collect. This will help me to determine the statistical power of my experiment. I also need to determine what the effect size will be. If you're not familiar with effect size, it's related to the difference between the win rates of the 2 slot machines. Then what I'll do is, I'll take that, do some fancy power calculation, and that will tell me how many samples I need to collect. At this point, alarm bells should be ringing in your head. How do you know the effect size if you haven't even played any of the slot machines to begin with? That is just one of the many reasons why traditional statistical tests are very awkward. Okay, so let's say you do your fancy calculations and it says you need to play each slot machine 10,000 times. Now imagine this scenario. You've played each slot machine 5,000 times so far. Slot machine number 1 has won 3 times out of 5,000. Slot machine number 2 has won 4,000 times out of 5,000. So basically your prediction of the effect size was wrong. But in order for this to be a valid statistical test, in the eyes of a statistician, you must take your experiment to completion. You cannot simply stop your experiment at 5,000 and say, I think slot machine number 2 is better than slot machine number 1. That would invalidate your results. Yet another reason why traditional statistical testing is quite awkward. You might also want to consider a more serious scenario. What if you're testing a life-saving drug and it's been successful 97% of the time in your test group? Do you still continue your experiment, giving the placebo to the control group, which has no effect at all? Is that ethical? So maybe you say, we should throw out this traditional method and use a method that can adapt as new data is collected. This would be similar to what we originally did in this lecture, using our intuition. In this section, we will learn about how we can do that algorithmically and quantitatively, rather than just by mere feelings. What you encountered earlier in this lecture was 2 opposing forces. On one hand, you wanted to be like a good statistician and collect lots of data so that you could make your estimate more accurate. We call that exploration. On the other hand, we wanted to choose the slot machine that had the highest win rate so that we could earn more money. We call that exploitation. And because these 2 objectives oppose one another, we call this a dilemma. Hence the term explore-exploit dilemma. Alright, so as I mentioned, the rest of this section is devoted to algorithms that will solve this problem. We'll be looking at 4 main algorithms. The first is called epsilon greedy, which is something we'll be using all throughout reinforcement learning, in this course and others. The second is called the optimistic initial values method. The third is called UCB1. UCB stands for upper confidence bound. And finally, the fourth is called Thompson sampling, which makes use of Bayesian statistics. Sometimes people will call this the Bayesian bandit method. And just so we don't lose sight of the big picture, these are all algorithms you can use in place of a traditional A/B test in your software system. They are methods that overcome some of the awkward problems like effect size, wanting to stop your experiment early, and the controversial p-value. These methods are adaptive, meaning that they learn on the fly, which might be considered advantageous, especially in high throughput, online business settings.